We're working with volumes of solids with known cross-sections, and we're going to jump right into this first example. I gave you the handout for that, and we're looking at a mathematician making a paperweight so that its base is the shape of the region between the x-axis and one arc of the curve y equals 2 sine of x. Now, we know the sine curve does something like that. And since it's y equals 2 sine of x, then I know the only difference is it comes up to 2 instead of just going up to 1. All right? But we said we're only looking at one arc of this thing. Okay, so we're only looking right here. Now, let's keep reading. Each cross-section cut perpendicular to the x-axis is a semicircle whose diameter runs from the x-axis to the curve. Okay? So what we've got, I'm going to draw this a little bit better three-dimensionally, and this is on your paper, is we've got the y equals 2 sine of x kind of looking like this, and then we have these semicircle cross regions, all right, reaching up to the curve. All right, so when we're cutting this thing, to add up all of our little volumes, we are cutting a semicircle. All right, so you're actually slicing off, instead of a whole cylinder, you're slicing off half of a cylinder. Okay, something like that. We're slicing off half of a cylinder. So if I wanted to find the volume of that little cylinder, that half cylinder, we still use the same formula. It's still pi r squared h, but I'm going to need to divide it by 2 or multiply it by 1/2, whichever way you think of it. All right? And remember, the height in all of these cases that we've been working with, that gets represented by dx. Okay? Because we're cutting off an infinite number of these little half-cylinder regions, so we just let that be dx. All right? So the radius, okay, we need to talk about. Technically, the radius would be this, right? Well, let's think for just a minute here. Isn't the radius going to be, and of course, couldn't I draw it up here like this? I mean, the radius can go anywhere. If you look at this thing right here that I drew, this is the diameter of my semicircle. So isn't the radius half of the diameter? Right? The radius is 1/2 of the diameter. And isn't the diameter the function value? Right? Isn't this distance, okay, isn't this distance right here going to be the function value? All right. So what I have now is that the radius is 1/2 of 2 sine of x. All right. That is my radius. Now, do you see the 1/2 times the 2 cancels? Okay, so these 2's go away. So my radius is just equal to the sine of x. And now we are ready to go ahead and start finding my volume. Because remember what I said, I'm just using, let's come back here, my volume is going to be this, pi r squared h divided by 2. So let's translate that into an integral. Pi will be out here, r squared h is the dx, okay, divided by 2. Let's pull that 1/2 out in front, just like that. Now, we just found the radius, right? Didn't we say the radius was sine of x? So now I have the volume equals pi halves times the integral of sine of x quantity squared dx. Now, we don't have our limits of integration yet. Didn't we say 1 arc of the sine curve? So we don't really need a graphing calculator for that, do we? This is 0. What's this? Pi. Okay, this is pi. So there's my limits of integration. 0 to pi. So now we have a integral that we've seen before where I have this sine squared x. Let's go ahead and keep moving. Volume equals pi halves times the integral from 0 to pi of sine squared x dx. Looks to me like we need to use the power reducing identity, our old friend. So this thing is going to become 1 minus the cosine of 2x over 2. I still have my pi halves out here. I still have my integral from 0 to pi. So we said using that power reducing identity, we always want to bring it out in front. So I'm going to have a 1/2. I'm going to have this 1/2 times this 1/2, which is going to make it 1/4. So now I'm going to have pi fourths times the integral from 0 to pi of 1 minus the cosine of 2x dx. All right. So we can split that up into 2 integrals. The pi fourths will be times the whole thing. I'm going to have the integral of 1 dx minus the integral of cosine 2x dx. My limits of integration are still the same. Let u equal 2x, du equals 2 dx. We've done this before, so I introduce a 1/2. So now I've got the integral of 1 dx minus 1/2 times the integral of the cosine of u du. So this is going to be x minus 1/2 the sine of, I'm going to put my u back in, 2x. And it's going to be evaluated from 0 to pi, we said, and then it's going to be multiplied by pi fourths. Okay, so let's see, pi fourths times, let's see, pi minus 1/2 the sine of 2 pi, that's the first part, minus 0 minus 1/2 the sine of 0, so that's just going to be 0. The sine of 2 pi is 0, so I just have pi fourths times pi. So that's going to be pi squared over 4. And that will be my answer to the volume of that paperweight. All right? Now, the next example that I want to look at is out of your book because I wanted you to see kind of the setup, page 410, and I want to look at number 1, part B, in the exercises section. It says in exercises 1 and 2, find a formula for the area of the cross sections of the solid that are perpendicular to the x-axis. Number 1 says the solid lies between planes perpendicular to the x-axis at x equals 1 and x equals -1. The cross sections perpendicular to the x-axis between these planes run from the semicircle. Okay, so what we've got is we've essentially got, they say the semicircle y equals the square root of 1 minus x squared and y equals the negative square root of 1 minus x squared. We've just got a circle is what we've got with a radius of 1. Okay? The radius is 1 of that circle. And let's just keep going though. Part B, the cross sections are squares with bases in the xy plane. Now, if you notice the instructions, they just said find a formula for the area of the cross section. So we're not even going to finish this problem right now. We're just going to find the first part of that slice. So what we've got, I'm going to draw this kind of three-dimensionally. We've got this thing kind of like that, and the cross sections are squares, which you see there drawn in your book. So when I make a slice of this thing, what I'm slicing off is a square. All right? Now, what would one side of the square always be? If I want to look at one side of the square, what would it be? Well, don't we have to do it in terms of the function? Right? If I look at one side of the square, well, a square is symmetrical. This thing's centered right at the origin. So I've got a distance here and a distance there. Wouldn't you agree that one side of the square would be equal to 2 times the function value? Does that make sense? All right, I'm going to pause the video. So in this case, you know, if I come back up to my original circle up here, let me explain this a little bit more. This distance right here is the square root of 1 minus x squared, right? Well, since the circle is symmetrical, and I didn't do a great job drawing my circle, it should, you know, come down a little bit further. That distance is going to be the same thing as this distance. So this is also the square root of 1 minus x squared. I know it's the negative, but that doesn't matter. And the reason it doesn't matter is because when I'm working with the side of a square, if I find the area, I square it. Okay? So if I add these two together, that's where I come up with this 2. Okay? So one side of the square is 2 times the square root of 1 minus x squared. How do I find the area of a square? Isn't it side squared? Right? So there's my side. The area of that cross section is going to be 2 times the square root of 1 minus x squared, that whole mess, squared. All right? So that would be, let's clean that up, that would be 4 times the quantity 1 minus x squared. And we have answered number 1, part B. All right? Because all it asked for was the formula for the area. Now, what if I wanted to find the volume of this mess? Okay? What if I wanted to find the volume of this mess? And I'm continuing the example even though the book doesn't ask you to do this. If I wanted to find the volume, okay, well, let's go back here. What am I slicing off? I'm slicing off little squares, right? So how do I find the volume of any box? Isn't it the area of the base times the height? Okay, the volume of any box is the area of the base times the height. Well, my height is dx, and my area of the base, didn't we just find that out? 4 times 1 minus x squared. All right? So guess what? We're ready to find the volume of this thing. It's going to be the integral of 4 times 1 minus x squared dx. Okay? And then my limits of integration, because it's a circle of radius 1, is going to be negative 1 to 1. And we could get that from our picture, our original picture. this was -1, and this was +1 over here. All right? So we already verified what the area was, so we were also able to use that in finding my volume, if I wanted to find the volume of that figure. Which, remember, all of these figures have a flat base. They're kind of like a paperweight. Okay? So then this is a pretty easy one to finish. I'm not going to finish it right now, and we will stop there for today.